Okay, let's take a look at some of our problems in section 6.1. And these are problems that deal with areas between curves. So the first problem that I have listed for you here provides us actually a graph of two functions, y equals x squared and y equals 2x over 3 plus 16 thirds. And it's asking us to find the area of the shaded region. So for this type of an example, we are going to have to divide our region in two. So I will start by, let's see if I can get this as straight as possible. I'm going to go ahead and divide my region in two right here. And I will call this first half, call this A. We'll call this region A. And this is going to be a little tiny, but we'll call that region B. All right. So here we go. So for region A, the integral here that's going to give me the area of that region is going to be the integral from a to b of top minus bottom dx. So first of all, we're going to set this up as an integral with respect to dx. So there's a clearly defined top and bottom here. The function on top, the red line, y equals 2/3 x plus 16 thirds, minus the function on the bottom is going to be the x squared. So top minus bottom. And then we have to make sure that we integrate this over the interval where this region exists. So this would be from -2 to 1. And again, note, this is where I'm going to go ahead and put my 1 in there because that's where these two functions intersect. All right, so we can go ahead and evaluate. The integral here would be 1/3 x squared plus 16 thirds x minus 1/3 x cubed, or x cubed over 3. And we're evaluating from -2 to 1. So again, just simply following the fundamental theorem of calculus, we will plug in the top minus plug in the bottom. This is very methodically, plug in top minus plug in bottom. And definitely at this point in time, you can go ahead and stick this on your calculator. I get an answer here of 12. All right, so now let's look at the second region, region B. Again, there's a very clearly defined top and bottom function here. So we set this up in the same way. In this case, it's going to be the integral from 1 to 2. So note those bounds. And here, the function on top, again, this is the linear function y equals 8 minus 2x. And then the bottom function, again, is the function y equals x squared. So again, top minus bottom is the way we're going to set this up. And then if we evaluate, we will get 8x minus x squared over 2 minus x cubed over 3. And again, we're evaluating, and I see that I made a mistake here and plugged in an incorrect bound. So this is supposed to be 2. Hopefully I didn't carry that mistake through. Plug in top, I did not, just a little typo here. So plug in top minus plug in bottom. And again, at this point, you can definitely use your calculator to evaluate. When I evaluate, I get 8/3. And then just as a final answer here, we want to go ahead and add those two together. So our total area, A plus B, is going to be 44 over 3. And I'm going to just note units squared on my answer because that says that we know that we just calculated an area. All right. Let's take a look at the next problem. It says, sketch the region enclosed by the given curves. Decide whether to integrate with respect to x or y. Draw a typical approximating rectangle, and then find the area of the region. So here I will start by actually just providing a graph. So here's a graph of my two functions, y equals 3 times cosine of x, and y equals 3e to the x. The third function that's given here, x equal to pi halves, we are going to use that as our upper bound, right? So this is going to help us bound our function. So you can see this region can very clearly be calculated as, again, a top minus bottom here. So area here will be the integral of top minus bottom. So this will be an integral with respect to x. All right, so when we set this up, this will be the integral from 0 to 1/2. A 1/2 here is given, so that bound is given. We did not have to calculate it. Of my top function here, 3e to the x, minus the bottom function, 3 cosine of x dx. All right, we just go through the steps of evaluating. The integral of 3e to the x is just 3e to the x. The integral of minus 3 cosine of x will be minus 3 sine of x. And again, evaluate from 0 to pi halves. All right. So again, just very methodically, plug in top minus plug in bottom. If you want to give your answer as an exact value, you will do this by hand. I get 3e to the pi halves minus 3 minus 3 minus 0. So simplification there gives 3e to the pi halves minus 6. That is about the cleanest exact answer that I can give here. But if you want to put your answer into a decimal form, I get 8.43143. And again, I'm just going to tag that units squared just to show that I realize that this is actually an area that I just calculated. All right, let's look at the next problem. All right, so for number, I don't know what number this is, but the problem says, sketch the region enclosed by the given curves. Decide whether to integrate with respect to x or y again, and then the same as before, draw a typical approximating rectangle. So the functions that are given here, x is equal to 4 minus y squared, and x is equal to y squared minus 4. So the first thing that I want to do here is go ahead and just graph. So I use Desmos, so you can use your calculator to graph. If you use your calculator to graph, you will need to solve each one of these equations for y. And then, so you're going to actually end up typing in 4 equations if you solve for y. You can use a different graphing device, like I said, like Desmos, and that allows you to enter functions in terms of either x or y. Either case, this is what I get when I enter these. And I called these, instead of x, I called them f of y and g of y, just so we can sort of refer to the difference between the two. All right. So in this case, there's not a clearly defined top and bottom, but there is a clearly defined right and left. So I'm going to set up this integral as the integral of right minus left. When we integrate this way, we always integrate with respect to y. So note that this is a dy type integral. So in this case specifically, the integral of right minus left, this will be the integral of f of y minus g of y dy. Right? Specifically, this will be the integral going from -2 to 2. And note, in this case, we want to go ahead and look at the y-axis. To go ahead, it didn't work very well. Let me use a highlighter. We want to look at the y-axis to go ahead and find our bounds. So we're now integrating on this interval right here. So from -2 to 2. All right. And it's going to be right minus left. So 4 minus y squared minus y squared minus 4. And note that I keep both of those two functions in parentheses because the negatives will need to distribute. And so with that said, it may be good to put in just one step of cleaning up before you start integrating. If we remove those parentheses, we're going to get the integral from -2 to 2 of minus 2y squared plus 8 dy. All right, let's go ahead and integrate. The integral of -2y squared will be -2y cubed over 3, or -2/3 y cubed. The integral of 8 is going to be 8y. And again, remember our bounds, we're evaluating from -2 to 2. Fundamental theorem of calculus says we are going to plug in top minus plug in bottom. So just very methodically, plug in 2 into the entire quantity minus plug in -2 entire quantity. Again, at this point, you can plug this into your calculator. If you try to evaluate by hand, I get 32 over 3 minus -32 over 3, which of course will give me a positive 64 over 3. And again, I'm going to note that unit squared just to show that I know that this is an area that I just calculated. So for this problem, I did want to just really quickly show an alternative way that you could have done this. Again, just because of the symmetry here, again, if you look at our graph, so we have these 4 symmetrical regions, like the region that is shaded right there. So if we just look at 1/4 of that region, you see that we can really easily integrate as a right minus left or as a top minus bottom. So if you are willing to just rewrite these equations so that you get an equation y equals square root of 4 minus x. So now we have f of x function. We can integrate this with respect to x as a top minus bottom. So you could have set this up in this way, all right? And so this would have been the integral from 0 to 4 of the square root of 4 minus x dx. So in this case, we would have had to use a u substitution. So I would here let u be equal to 4 minus x, which makes, let's see, du would be equal to negative dx. So negative du is equal to dx. All right. And then, let me try that again. So that would give us, after substitution, we will have negative the integral of the square root of u du, which becomes negative the integral of u to the power 1/2 du. When I integrate, this will be negative 2/3 u to the power 3/2, or we can then we can back substitute. So this would be negative 2/3 times 4 minus x raised to the power 3/2. All right. So once you're done back substituting, you can evaluate on the original bounds. Note, you could have also converted the bounds to bounds with respect to u, and you could have done it that way. I chose to convert back to x, and so I'm evaluating with my bounds with respect to x. So fundamental theorem says we will plug in top minus plug in bottom. And again, at this point, just very methodically, go ahead and evaluate or plug in your calculator. I get 0 minus negative 16/3, which is going to give me positive 16/3. So the answer is the same as before, well, almost the same as before. One more thing that we need to do, this is still 1/4 of the region. So to get the entire region, I would need to multiply the 16 over 3 by 4.